Welcome everybody to this taster lecture, and today I'd like to present to you a taste of computer architecture, and we're also going to have a look at a student software project. So I'd like to begin by giving you a glimpse at some of the topics that you will study if you're at Leicester and you take the computer architecture module. You'll spend quite a lot of time studying how computers perform arithmetic, and we'll be looking in particular at the hardware inside a machine that supports the calculation of arithmetic. So that's a topic that we'll look at in some detail, and it really underpins how computer processors work. So once we've done that, we'll then go on to spend some time studying simple computer processors. And one of the things that you'll learn is the basic idea that a computer processor is made up of two components. There's the digital hardware, so this is the device that you hold in your hand, and then there is the software part. So this consists of a programming language and a program, and the instructions in the program are executed on the hardware. So understanding these kinds of things in more detail is something that you'll do in this module. We'll spend quite a lot of time looking at the fundamentals of digital hardware. So we'll be studying individual hardware circuits in some detail. And we'll also be looking in more detail at the software languages that run on the hardware. And there are two examples that I am mentioning here, MIPS and ARM. You may well have heard of ARM because that's a language that quite possibly is running on your phone right now. So we'll look at these two languages in some detail. And then towards the end of the module, we're going to look at the details of more complex processors. So I'm going to do something really risky, but I hope also fun in this introductory taster lecture, which is I want to give you a flavour of the whole module. So let's see if I can actually do that. So how do we start things off? We start things off by looking at elementary hardware. If you look just here, I've drawn a little box. It's labelled plus, and I'm mentioning that it's an add circuit. So the idea is that this box is a little piece of hardware that you might find in your PC or your device. And you can see a very simple idea here. 4 and 5 are input, and as you would expect, 9 is output. So this is an example of a basic hardware circuit. And here we have subtraction. So 7 and 11 are input, -4 is output. Another example, slightly different, multiplication. So here we've got 3 inputs, and we've chosen values of 2, 2 and 2, and so we get an output of 8. I've labelled the arrows data bus, or sometimes we say data channel. And the idea is that inside the machine, data values, like the numbers that we see here, can flow around the hardware inside the machine. And I've illustrated data flow in this final example just here. So there's data flow indicated by the dotted green arrow. This is an example where I've built a bigger circuit in the pale grey box out of 2 basic circuits. The basic circuits are multiply and subtract 5. So here the idea is that if 3 and 4 are supplied as inputs, the data will flow along these 2 data buses into the multiplication circuit. That outputs 12. 12 is fed straight into the subtract 5 circuit, and then we get 7 as the answer. So these examples here may look very straightforward and simple, but the idea is that a complex computer processor can be built out of basic circuits rather like the ones that we're seeing here. So let's move on and have a look at another example. So here we're looking at something called a data path. And I've got a computer instruction, add y(x)(3). Let's first of all talk about the instruction. So the rough idea is that the x and the y are variables. So you can think of them as letters standing for unknown numbers. And let me tell you how this instruction executes. What happens is that we take the value of x, add 3, and store the answer in y. So now what we're going to do is to try to look at a little piece of hardware which will allow the execution of this instruction. So let's begin to look at the hardware. Just here is a little box. I've labelled it memory register, and the idea is that this is a little piece of computer memory and it stores the value 5, and we can also see a little box here with 4 in it. How is that connected with the variables? The idea is that if you start out with this high-level instruction involving the x and the y, there's a bit of magic that happens, and somehow x is associated with a little piece of computer memory, and what's stored there is the value of x. So in this example, x is associated with this piece of computer memory, so the box containing 5, and y with the box containing 4. Inside the machine, we have to be able to locate or identify particular pieces of memory, and we do that using addresses. So if you think of the boxes as houses and the two addresses, so here an address of 0, an address of 1, that's a little bit like the number that's perhaps on your front door. So obviously your house number acts as part of an address so that people can find you. So in this example, x has address 0 and y address 1. What else have we got? We've got an adding unit, so that's a basic circuit, rather like the one we were just looking at. I've labelled it ALU. I've crossed out the L. I'm not going to talk about that in this particular talk. This stands for arithmetic unit. And the idea of an arithmetic unit is that it's a piece of hardware that can do, for example, addition or subtraction or multiplication. So we can choose what it does. In this example here, the ALU will just simply do addition because we're executing an add instruction. If you look down below, we've got some details of the execution of the instruction. Before I go into those details, let's have a look at the picture of x. You can see it's changed. I've chopped it up into little pieces and written some 0s and 1s down. Next key idea is that numbers, like the 5, are stored inside the machine as binary numbers. And these are sequences of 0s and 1s. And some of you with a bit more background will recognise that this is the correct binary value that corresponds to the number 5. So what happens at execution? You've probably already looked down at the bottom of the slide. So the number 5 will flow from this memory register along this data bus and into the adding unit. The number 3, that's appeared magically from nowhere, but again, I'm going to leave that as a teaser, unexplained. If I do have the 3, that number also is fed into plus. That circuit produces the data value 8, and then we have data flow along this bus, and then the value that we've calculated, 8, that then is stored in the memory location associated with the variable y. Now its original value was 4, so that's changed to the value 8, and then that's the end of the execution. Okay, let's press on. That example had an arithmetic logic unit, and here's an example of a slide where we look at ALUs in more detail. This is just a flavour, and I'm just going to point out 1 or 2 key ideas to you. So here and here are the input buses. So we had examples just now where 2 numbers were input on these buses. And in fact, some of you may recognise that in so-called unsigned binary, the input just here is in fact the number 5 and the number here is 7. But again, this is just a teaser, so I'm not going to really explain to you here why that's the case. The one thing that I do want to look at in detail is to show you that when you magnify a picture of the data input bus just here, it splits into 3 wires, which I'm pointing at. And the way the machine stores binary is that each of these wires will have a voltage of either 0 or 1. So I've illustrated that just here. So in the lower example, each of the 3 wires, so this one, and this one, will have a voltage of 1. Again, this is a little flavour for this slide, so I'm not going to go into any more detail, but it's in the video and you might like to look back at it. What I do want to explain to you here is a very high-level view of how a little program is executed on a processor. So what is a program? Here in the middle of the slide, I've got some memory locations. So you can see the boxes and they have addresses. So address 0 to 18. Inside each box is an instruction. So we've got instruction 0, instruction 1, and so on, right up to instruction 18. So the idea is that each of these instructions you can think of as being a little bit like the add instruction that we've seen. So how is all of this coordinated? The memory that I'm looking at in the middle of the picture here is actually in the computer's main memory. In the processor, there are 2 other pieces of memory, registers we call them. There is the IR, that's the instruction register, and there's the PC, program counter. So what's the basic idea? The instruction that is currently being executed in the processor, rather like we saw the add instruction being executed, that's stored in the IR. So currently I16 is executing. The program counter contains the address of the next instruction to be executed, and we sometimes say that it points to the next instruction. So you can see that very visibly in this picture. Once I16 has finished executing, what happens is that the instruction that we currently point to, I, that gets copied into the instruction register. In fact, we say it's fetched, and then I will execute. And as I executes, what happens is that the program counter is then updated to point to the next instruction to be executed. And in this example, it happens to be the instruction at address 18. Okay, so hopefully that gives you a little bit of an idea about how a simple program composed of a sequence of instructions is executed on a processor. We basically pick out each instruction one by one and execute them. This is a summary slide, and what's written here is simply a summary of everything that I explained when I was talking about the last 3 slides. So this is another example of how we would learn material on the module. I will speak over some slides where we have some dynamic illustrations, rather like the 3 slides going forwards here. And then there's a summary slide which the students can look back at. So I don't need to read over this slide, but it's here as a summary if you'd like to look at it later on. Oh, what do we have here? Now, I did say that I was taking a fun risk here in that I was trying to give you some ideas about the whole module. What do we have here? We have a slightly more complicated data path. You might be looking at it and thinking, oh my gosh, that's far too difficult to explain in the time available. I agree. But let's have a quick look at the picture. Just here is a box and it's labelled registers. So inside this box are little pieces of computer memory and each one is a register. But you've got an idea about that. We've already seen some registers. We had the register for variable X and Y. And here's the ALU, and you can see that there are 1, 2 input buses, and this bus that I'm pointing at, labelled ALU result, is where the answer comes out. So if we have our good old 5 here and 7 here, then we'll have 12 here. Again, this is just a flavour of the things that you'll look at, so I won't spend any more time talking about this particular picture, but it's a flavour of what's to come if you take the module. This slide and this slide are written summaries describing how that data path that we've just looked at works. So again, this is to just give you a feel of how we're presenting material to you. In the real lecture, I would spend a lot of time simply data path picture up, this one, and I would talk about how it operates very carefully, and there would also be some data flow that's illustrated, and I often use a tablet to do that. Now we get to a more complex setting. So the students will study a data path, we've already looked at that, with something called a control unit. The basic idea is that a processor is made up of a data path and control. I've tried to give you a flavour of the data path, and the control unit is a part of the hardware that simply organises the data flow in the data path. Students study a MIPS processor in detail, but there are processors that are really quite similar, but we won't talk about those here. And then finally, here's a picture of a MIPS processor. So again, let me just point out key things. In the middle here, you have your registers. So rather like the X and the Y that stored the values 5 and 4. So inside that box, you'll find the registers. Here's the main arithmetic logic unit. So we had an example where this was used just to do addition and to execute an add instruction. And I've mentioned the control unit. So this little box here in the blue will send out lots of what are called control signals along these blue buses. And those control signals end up in the hardware components and make sure that they operate or behave in exactly the required ways. So one example would be down below, there's something called ALU control. And if we wanted to do addition, a signal would flow along the data bus that I'm pointing at into the ALU, and that would make sure that the ALU does addition rather than, say, subtraction or multiplication. Okay, so that covers most of my slides. I'd like to give you some take-home thoughts, but we do have a little bit more to do in the next few minutes. So just stay with me, let me summarise, and then we're going to look at a student project. So question, what did I learn? I hope that I've shown you that a processor is composed of hardware and software. So digital physical hardware, and software consists of some instructions, a program that is executed on the hardware. Hardware is made up of something called the data path and control. The data path is composed of some computer memory, a little unit that can do arithmetic, and some data buses where data flows around the hardware. Data is stored inside the machine using binary. Binary numbers are sequences of zeros and ones, and very roughly speaking, inside the machine, these are set up in the hardware using wires and other components where you can measure a voltage of 0 or 1. And then software instructions in general are executed on a data path, so rather like the add instruction that we saw. So overall, what have I shown you? Well, we've just seen examples of slides that are taken from my level 1 module. And what we're going to do now is to have a quick look at a very cool student project. So a student produced a processor simulator. So I really hope that you've been inspired to learn more. I hope you find, as I do, that this subject is really exciting. And indeed, I hope that you've been inspired to apply to Leicester. What I'd like to do now in the last few minutes is to demonstrate this processor simulator to you. In order to do that, I need to unshare my screen, and if you'll allow me a couple of minutes, I'm just going to get things set up to show you the processor simulator. So first of all, let me unshare my screen. and I need to take down the slides behind the scene. And I'm just setting up the windows that I need on my computer to demonstrate the software. So I think I've done that. And now I can come back in, and in a moment I should be able to share my desktop with you. Okay, so hopefully now you can see this software simulator. So let me try to explain a few basic things here. If you look over on the left-hand side, there's a little box called PC. That's the thing called the program counter, and it supplies an address in memory to locate an instruction to be executed. Here's a box called instruction memory. So inside the machine, that's where the instructions are. And what's cool about this software is that you can see inside the instruction memory. So if you look on the right hand side, we've got some addresses 0, 4, 8, 12, 16. And then there are some instructions. And if you look where I'm pointing, you can see an add instruction. Now this looks a bit different to my add XY3. This says add $S3, $S1, $S1. All you need to take from this taster lecture is that it's similar to the instruction that we looked at. So 3 pieces of memory are specified here, actually. So the dollars are each registers. And what we'll do is we'll take the values in 2 registers, add them together and produce a result that goes into a final register. But I can't really show you all of the detail here in this taster talk. Just try to imagine that we've got a sequence of instructions here, rather like the ones that you saw during the taster talk. What I can do is to start to execute this program, and I can use the software to do this. So let me press step, and what's happened is that the program counter that started out with the value 0 has allowed that value to flow along 2 data buses, now in red, and in particular that value is now available as an address for the instruction memory. So that means that the instruction at that address should flow along this data bus and be set up ready for execution. So let me do the next step, and you can see that the instruction was passed along this data bus here, and you can see that we've got the add S3, S1, S1 just appearing. That was the instruction just here. Okay. What's missing from this picture is that there should be a data path, and that's just here where I'm pointing, but we'll see that appear in just a moment. Okay, so let me do another step. The number 4 has been produced, and that's going to be added to the 0 to produce the next address for an instruction to be executed. Step through. So now the 4 is the new value in the PC. Let's step again. That value 4 is supplied as an address to the instruction memory. So this should cause the next instruction, which you can see is add $S4, $S1, $S0. So this instruction here to be passed along this bus and into the processor. And you can see that happening here. What we can do with this software is to actually animate the whole process so you can really see dynamic data flow. And that's what I'm going to do for you here. Let's just resume execution. And now you can see data flow for real in this processor. So now 8 is coming into the instruction memory, and this subtraction instruction, which you can see here is at address 8, was presented for execution. Now the instruction at address 12 is appearing. And if you look at instruction memory, just here, you can see that the address 12 is highlighted, and in just a moment, it will be address 16 happening now. And let's just wait for the final data flow. The final instruction here says exit. And when that's selected, everything finishes. Okay, so to finish off this taster talk, what I'm going to do is to bring up another simulator. And wow, here is a picture of a much more complex processor. Okay. We've got the same instructions to be executed here. And just to finish up this taster lecture, all I'm planning to do is to start execution and just a little bit of fun for you to watch the execution of the instruction where data flow occurs around the processor. There's lots more you can do with this software. You can look at the binary forms of the instructions as well as these symbolic forms. I won't do that here, but you can do that. You can play with the speed in which the data flow occurs. You can pause execution and you can resume execution. And just to finish up the taster lecture, let me just point out one final thing. I'm just going to let it run for a moment more. So right now there's a value being fed to the PC. So pause it. The value 4 is coming down here towards the program counter. That will then be fed in as a new address to instruction memory. And that's going to cause this green line just here to flip to the instruction with address 4. So if I resume, that's just happening now. Here comes the instruction and we've flipped to address 4. Let me resume. Let me show you one final thing. From the instruction, there's a piece of data just here that's being fed into the control unit. Remember I told you that the control unit organizes everything. What the control unit will do is send out lots of tiny little binary signals to lots of other components in the processor to make sure they work in the correct way. So what you should see when I start things up is a number of separate little pieces of data suddenly all flow out of the control unit and whiz around the hardware to individual components to control them in the correct way. So let me just do the resumption, and here we go. There are all the little, in fact, many zeros in this particular case. They all found their ways to separate components, and now there's some arithmetical data flow taking place. Let's pause this. So that's the end of the taster lecture. I do hope that you have enjoyed it. I've tried to give a real flavour of the kinds of things that we do in the computer architecture module. You've seen some example slides, you've seen me explaining things, and you've seen an example of a student project. So I hope you've enjoyed the lecture. And as I said earlier, I hope that that's inspired you to learn more. And I look forward, hopefully, to seeing you as a student at Leicester. So bye for now.